All right, so let's talk more about how you train these deep neural networks. Now, in the previous chapter, we talked about artificial neural networks with just a few layers, like 2 or 3 hidden layers, and they're appropriate for some things like sorting those clothing images into the right categories. Uh, I'm not seeing a green border around this. I'm not entirely sure I'm sharing my slides correctly. Let me just restop and restart the share to make sure it's right. Desktop 3, okay. All right. I guess it's right. It just doesn't show the border. Anyway, all right. But now, more complex problems, you might have 10 layers with a lot of connections. And so this will be a problem. And a few problems come up when you have deep neural networks. In particular, vanishing gradients is the one we're going to talk about a lot here. And this may lead to related problems, training being very slow, or you don't have enough data. And another issue is, of course, if you have millions of parameters, in principle, you can totally overfit the training set. If you had 1,000,000 parameters and only 500,000 data sets, then you could hit every data set perfectly by overfitting, and that's not really what you want. You want to learn the trend of the underlying phenomenon, not the noise in your particular examples. So we'll talk about the vanishing gradients problem and ways to schedule the learning rate and how to regularize these things. So this is a fundamental problem. If you have a sending in some data, and then you have a desired output, and you have many hidden layers, with backprop, as we talked about it, you'd start with random values for all these parameters, of which there are probably hundreds of thousands, and then you would take the output and do a partial derivative, figuring out how much each parameter affected the answer for a small perturbation, and therefore being able to figure out which direction to move the parameters to make it fit better. But the problem is, obviously, the weights on this layer will immediately affect the output, but changing the signal from these layers probably would have a much smaller effect on the output because all the later layers will wash it out. So the effect is only the last couple of layers have a significant gradient, and these have almost no gradient. Changing these by a little bit would have almost no effect on the output. So all you're going to do is train these layers, and these layers are never going to learn. That turns out to be, that's the vanishing gradients problem, and it turns out to be very serious. And under some circumstances, you have exploding gradients as well, where one side is in it. But the general problem is the different layers may have different effects on the output, and therefore they'll learn at different speeds. So when you go through a series of steps, you're really only training certain layers, and you're not really training the other layers. And this is so serious that people abandoned deep neural networks in the early 2000s because it seemed impossible to train them. However, it was figured out in the 2010s. So here's the problem. If your activation function looks like this, then you only have a slope to learn here. And if the signal gets too large, you're up here in the saturated level where changing the signal doesn't have any effect on the output. And the same thing if your signal gets too small, there's only a limited region where you can actually effectively learn. So what you do, one thing is to use Glorot initialization, where you calculate number of inputs and number of outputs, helps you choose what weights to start from to make sure that your weights are in that desirable area where there is a significant slope. That helps. And there are various different activation functions you can try to calculate. Depending on your activation function, you can choose what initial values of weights will increase your chance of being in a good part of the activation function. So there is a slope. And there's another one is if you use this common one, rectified linear, whatever it is, where you have completely flat on this side and then just a slope up there, then of course, as soon as you pass below 0, there's a complete slope of 0. No longer matters what the input is at all here. So the effect of changing this parameter is 0. And you can't learn at all. You can't even tell which direction to change this parameter. So this kind of function that has a totally flat region makes it very hard to train your neural network. So it's better to put a slope in that region. So there is always a slope. Now, the only problem is you have a discontinuity at 0, and that can lead to situations where it bounces back and forth across there. But it's a lot better than just having it completely flat on one side. So there are other functions people like where you use a mathematical equation to have a smoothly varying system here, which give you a larger region of desirable slope so you can learn. But the real problem here is normalization. Now, if you use this particular function, scaled ELU, this particular one here, then that mathematically will self-normalize. If you have a multi-layer perceptron, then it will automatically always move to a good spot and learn efficiently, but it turned out that that only applies under certain relatively strict conditions. So in practice, most of the neural nets that people were making did not really obey these rules, and it didn't work. So there's other functions that have been tried here to try to create a activation function, which is the input, how various inputs affect the output. And under certain conditions, they work. But the general solution is normalization, where you explicitly normalize each layer. Now, remember we talked before how if you have multiple parameters, and one of your parameters is in a unit where it's in thousands and the other parameter is in ones, that will bias the learning and generally foul up your neural net. And now it turns out the same problem is true of the intermediate signals. You want to make sure that the signal coming out of each layer is of the same scale. So one layer is not having a much larger contribution to the output than the other. And that's what happens here. You use batch normalization. So you have a layer and then you have a batch normalization, which will just scale it so that the output of the layer above it is of a certain size. And after each layer, you normalize it again. And the batch normalization means it takes a limited set of samples of your data and does a calculation just to determine a scale for this output. So none of these layers is going to be allowed to have a very large or a very small contribution to the end result to make sure they can all learn. That's the thing. Now, for short models like this, it doesn't matter. But for deep networks, you really have to have this normalization step after each layer to avoid the problem of vanishing gradients. And so then it'll look like this. And the normalization itself has some parameters, but it's sort of the same number of parameters every time. It doesn't matter that much. All right. And there are mathematical expressions that are used to perform the batch normalization and all these terms defined here. I don't really care too much about the math here, but the concept is important. Good. I see in the chat there's discussion of the random, which is fine. Randomness is another issue. All right, so you recalculate the batch normalization for each batch, and you then, what it does is it calculates a moving average of the mean and standard deviation at each layer and uses that after training is done. So you get, you learn reasonable scaling values there. And it turns out to be extremely important. If you do the batch normalization, so each layer is having a similar contribution, then you can converge in 14 times faster, less iterations. Now there's more calculation in each iteration because you have to calculate not only the layers, but also the batch normalization, but it turns out to be much more effective. All right, so there are hyperparameters to control this. Momentum and axis are used to control how it calculates those scaling factors in the batch normalization, but it is very commonly used. And another one is gradient clipping, so that during backpropagation, when you figure out what direction to go, you never allow the gradient to get too high, so you don't allow one parameter to be overemphasized. That's another way to, an alternative to backpropagation is just to prevent any one parameter from being given too much significance when calculating which direction to go. Now, there's another technique, which is kind of led me down a blind alley when I was preparing these projects. The book talked about this, where what you would do is take a model that somebody else has trained or somebody's trained for a different task, and you reuse some of the layers. So if you want to do some kind of visual output, like you're trying to discriminate those letters or numbers from one another, you might take a model that was trained to recognize faces. And what you'll figure is, I feed in a photograph, the first two layers are going to be doing something like detecting regions of solid color and circles and edges or something. And then up here will be the stuff specialized to faces. So you could just reuse the pre-trained layers from a different task on here, because probably the same higher order combinations of dots would be useful here. That's the idea. And then when you're training it on your specialized task, you only train the top layer or two, figuring that the lower layer, we're probably finding underlying primitives that are still useful. So that's the idea. So you freeze all the reused layers, then unfreeze the one or two layers, and just train them. So that's called transfer learning. And so it doesn't work well with small, dense networks. It works better, of course, with networks that have a lot of layers. So then you might reasonably assume that the lower layers are doing generic things like finding edges, and the top layers are the ones that are finding larger scale features that might be specific to that task. That's the idea. And so you train an unsupervised model on unsupervised data, like either an autoencoder or an adversarial network that tries to discriminate real data from fake data, or these other techniques we've talked about, like masking part of it. These are various models. And then you reuse the lower layers of that model for your new task. This was popular in the early 2000s. And so they used greedy layer-wise pre-training. This is another thing that was popular. They would train only one layer at a time. You do as well as you can with one layer, and then you freeze those weights and train the next layer alone and the next layer alone. Now, what we're doing is training all the layers together. But this is a technique that was used in the early days. So for face recognition, if you have only a few pictures of the individuals you're trying to learn, then you just pre-train on a lot of random pictures, and the lower levels of that model will probably be useful for the new one. That's an idea. And for natural language processing, you just start with a model trained on a heap of text from the internet, and then train the higher levels on the particular data you want. And like I say, this led me down a blind alley because this is what I thought was necessary to make products like Microsoft Copilot. What I thought from this textbook is that they said Copilot takes a foundation model trained on all the internet, and then it includes your custom company data. And from this chapter, I was under the impression that Copilot retrained the upper layers on your data, but that is not how it works. What it does is it uses this Microsoft Graph system to look up relevant information from your files, and it just adds it to the query. It does not retrain the model. This is considered more effective. The retrieval augmented generation is the more popular way to solve this problem of how do I add specialized data to a foundation model. And this is the old way to do it, and this is the new way to do it. All right. And so you can have semi-supervised learning, as we talked about, which is at the heart of all these foundation models, where it has removed a word or a sentence from some text and then tried to predict the missing word or sentence. So it learns the structure of sentences and paragraphs and such. So then you can talk about how to speed up your training. If you choose good initial values of the weights, that helps a lot, as we were talking about. So none of your weights are down in the flat zone where the weight, that parameter is no longer having any effect on the result. A good activation function is good, so it doesn't have regions of flat where you can't learn. Batch normalization helps a lot, so that you keep rescaling each layer to keep it in the correct region, reusing part of a network. These are old techniques. And the new way is use a faster optimizer. Now, we've talked about stochastic gradient descent, where you just take little steps and you just keep taking more and more little steps until you hit the bottom. And all these techniques are just ways to vary the size of the step to make the learning faster. So this is a standard one. Regular gradient descent takes large steps when the slope is steep, and small steps when the slope is gentle. So if the slope is gentle, it can take many, many little steps and take a long time to get there. So momentum is where you include momentum from previous gradients, like a bowling ball. So the size of the current step is not just based on the estimate of the slope where you are, but remembering back a few steps. So the idea is hopefully you'll roll out of a local minimum. And so then there's something called the accelerated gradient that again looks ahead to try to figure out whether the slope is continuing to be steep in the future. And so you have the Nestoff accelerated gradient. You start here, and the actual downslope is there. But if you look ahead a few steps, you'll find that this is the best direction. So it will choose a direction that is not immediately the steepest, but that is the steepest over the long range. And so it can more quickly get down to the bottom. An ADA grad moves more closely to the global optimum instead of just going down the steeper slope. Another does essentially the same thing, adaptive gradient. So it works for simple problems, but sometimes it stops too early and is no longer recommended. RMS prop improves this by taking only recent iterations to calculate the gradient, and this was the preferred method, the improvement on AdaGrad, but then the even better one came out called ADAM, Adaptive Moment Estimation. And this just combines the previous features, momentum optimization and RMS prop, and it has four hyperparameters just to control the efficiency of choosing the step. And in practice, this is quite powerful. Then AdaMax modifies the loss function, turned out not to be worth the bother. And NADAM was another one that might be a little bit better than ADAM. ADAM-W added a regularization technique so that like friction, so it will have a decay factor. So the weight will go down at each training iteration. And so there's various recommendations for different categories of all these things. They're all just ways to make the convergence faster by changing the step size. And if you have sparse models where most parameters are zero, then what's considered best is to use this lasso regression, adding the sum of the absolute value of the deviations, and then you have a meta parameter here to control how much that contributes. So there's learning rate scheduling, which is how you change the learning rate. If the learning rate is too high, then the loss will go up instead of down because you jump out of the minimum out into the wrong area. If eta is too small, then you do learn, but very slowly. And if it's too high, there's very slow. What you really want is a nice smooth convergence quickly down to the actual perfect solution. All right. And so there's various ways to do it. You can drop the learning rate after each step. You can do it by a factor. You can have a constant learning rate for a while and then a different rate for the next one, and so on. There's just many ways to adjust the learning rate as you go ahead. And here's another one where you increase the learning rate by a factor of 10 for the first half and then decrease it for the second half. So first you jump all over, hopefully getting out of all the local minima, and then you can move down slowly once you've found what you could find with a big step. Various ways to do it. And then the issue of regularization. How do you avoid fitting the noise in the data in addition to the trend? And you can have these regularization functions where you add the absolute value of the weights or the square of the weights to avoid letting the weights get too big. And the most popular technique is just early stopping, where you just, as soon as it starts getting worse, you stop rather than optimizing it anymore. That's an easy way to do it. Then there's dropout regularization. At each training step, you ignore some of the neurons and let the others learn. This turns out to make a more robust network that generalizes better. All right, that prevents you from fitting so carefully that you're fitting the noise in addition to the signal. So in practice, you just turn off some of these neurons and use only the others for calculation now and then. So it doesn't focus on the details, but it gets the general trend. And you can use Monte Carlo that will use different random dropouts. And here's one where you force the sum of all the squared weights to stay below a maximum. All of these are just ways to smooth out the model so it doesn't focus on little details that go up and down quickly. So there's a summary of various times when you use these things and various recommendations for hyperparameters to use. That's the sort of consideration for real sophisticated models like the large language models. So I'm going to stop this one.